Hello, and welcome to this Nitrex webinar. Now I would like to introduce today's presenter. With us today, we have Jack Kaluki. Jack is a technical advisor at Nitrex. To read more about Jack today, please look at the speaker bio window right next to the main presentation window. And with that, I'm going to pass things along to Jack to get this webinar started. So Jack, right over to you.
Thank you very much, Katie. Well, good day, everyone. We are pleased to present the most recent improvements to Ferritic-Nitrocarburizing technology adapted specifically to gray cast iron brakes. The technology is not entirely new. You have probably heard that it has been employed since several years. It has new use right now because the transportation technology is undergoing many changes, and it is extremely rapid. Basically, we are all trying to stem pollution, and you probably heard years ago about the infamous Dieselgate. Following that, there were many studies of pollution, and those studies revealed that near transportation hubs and in large cities, combustion engines were actually not the biggest source or not the only source of pollution, especially for particulate matter, meaning dusts and such. Just a few words on Ferritic-Nitrocarburizing. The technology has been around for quite a bit, and it has been generally used to improve surface or tribological qualities of carbon steels. This is the main application of the technology. In essence, the process creates a white or a compound layer on the surface of components. This layer is usually composed of 9 to 10% weight volume of nitrogen and iron, which makes it a quasi-ceramic. One of the properties of this surface layer is to reduce corrosion and pitting corrosion. In carbon steels, the diffusion layer is not necessarily very hard, and it's not much harder than the core. The white layer contributes to most of the hardness. If you look at the two small diagrams completely to the right, on top what you see is your carbon steel, which has, as I said, very low hardness. The small letters that you see epsilon and gamma prime show two different phases of the white layer or the compound layer. Just below, you see another small diagram which shows hardness with metallic and nitrides precipitated in the case, and this contributes to the core hardness, to the case hardness. So you don't only have a white layer, but you also have a very hard diffusion case. So, going back to the infamous emissions, studies found that beyond exhaust particles, we are also breathing air contaminated with tire, road, and brake particles. The shocking conclusion is that if you would eliminate entirely, completely, combustion engines and combustion in transportation, you would still have a very large source of pollution from sources that we really don't think about. Actually, we don't think about since we eliminated asbestos from brakes. So we're thinking, today we don't have so many particles, which are very unhealthy for people living near transportation hubs and in cities. Okay, so sorry, small mishap. So here you go. So the exhaust particles are shown here, coming from those studies, and what you see, and it's very hard to make up looking from far at this slide, you have two lines. You have two types of particles, and you have a blue line which is decreasing, and this is the blue line of particles, showing particles coming from combustion of fossil fuels. So as diesel gets cleaner, or there is less diesel trucks and cars, and as you have better combustion in engines, you are lowering all the time those particles. The orange line, on the other hand, is showing something different. You see an increase of road non-exhaust. This is what's called the road non-exhaust, and it is compounded basically from brake particles, iron particles from discs and the drums, road wearing out, so asphalt basically, as well as tire particles. This is a summary of emissions, and what's very interesting in this summary is that the shift towards electric vehicles did not do much to reduce those particles, and this is where the increase comes from. Electric vehicles are typically somehow heavier than internal combustion vehicles due to batteries and other components. And by being heavier, they wear out tires and eventually the road to a greater extent. Also, what happens in electric vehicles is that most of light braking is done by regeneration, meaning that it is basically your sort of engine brake that you are using to recharge the batteries, and therefore you are not using brakes as much. Because you're not using brakes that much, those brakes tend to rust or be underused and emit particles. So here what we see is that if we eliminate exhaust particles from a hybrid vehicle, let's say, you would still have about 80% of particles emitted by the vehicle. So it's quite considerable. There was a study which was called Lobras's, a research project to try to identify the best technology to reduce particles emitted by vehicles. And obviously, the various solutions included ceramic coatings of rotors and pads. This is already done today on high-end vehicles, but it's extremely pricey. Then you have software to change the brake strategy. This software is used by most of the newest intelligent cars, mostly hybrid or totally electric cars. And you may also add a filter system to improve retention of particles. So as a consequence, you can use Ferritic-Nitrocarburizing as one of the most cost-effective means of reducing all kinds of pollution. Now, the idea of using FNC is absolutely not new, and it was introduced in North America for a very different purpose. The basic idea, and this is it was early 2010, I believe. The idea was to basically increase service life, reduce brake pad wear, reduce warranty claims, among others. So the reduction of the brake pad wear and increase of service life points to a very important fact. FNC really modifies the structure of rotors and reduces abrasion of the braking pads, thus less particles. What we don't really say here or show here, but you can relate that to slides further down my presentation, is that you have a rotor. Imagine a rotor covered with the white layer on FNC, and within the structure of the cast iron, you also have diffused nitrogen. What will happen is that with what you see is rust, obviously, but this rust may wear out after several kilometers or miles after you have been using brakes. What you don't see after it has worn out is that, and the surface may appear glittery, is that there are pitted areas. And those pitted areas, this is what the study really shows, is that those pitted areas contribute greatly to the abrasion of pads. So a seemingly glittery and nice disc may have been pitted, and if it's not really very significant, you may not notice it, but there is a huge impact on emissions. Now, this is a small study of stiction. Now, stiction is a funny word. It's a portmanteau word made up of static friction and strongly influenced by sticking, which is what happens if you leave your car with the handbrake on, or you leave your car outside for several days, and then you have the unpleasant surprise of not being able to move because the brakes are stuck. And what will happen afterwards is that once you start the car, you break free eventually. Obviously, you have damaged both the disc and the pads, and this is a huge contributor of emissions. Now, if you live in a very large urban area, there is a chance you may use public transportation, but still have a car parked for several days, perhaps in some area which isn't totally dry. And obviously, it's more of a problem in large cities, in underused vehicles. Still, those vehicles will account for a very large portion of emissions. So going back to how the process is done, you can see that on the surface of any nitrocarburized or nitrided layer, you do have what we call white layer or compound layer. It is called white not because it is or appears very often clear, but because to reveal that we etch it with a special agent in the metallurgical lab. And then all areas which are rich in nitrogen will appear white. So this is a much nicer picture. This is electron microscopy, so it allows you to look closer at that structure because it offers a very good explanation of what is really happening. So the nitrogen content in the white layer or compound layer influences both corrosion, resistance, and mechanical properties. The very top layer, or the epsilon, enhances corrosion resistance, and the gamma prime, which is just underlying, will improve mechanical properties. The very surface of the white layer, and you can see this in form of small bubbles here, seen oxide of FeXO, which is mostly Fe3O4, is magnetite. And this is a transformed layer. It is an oxide, but contrary to rust or what we know as hematite, magnetite is extremely compact and prevents corrosion. Furthermore, there is one very important note about white layers and corrosion. White layers are not really added coating on the surface. They grow up on top of a nitrided surface as the extension of the structure that is underlying. So all defects, plastic deformations, cuts, anything that is wrong with the structure, even high roughness, will influence the quality of white layer and provide areas where corrosion will start easier. So this is very important because the modified process that we have adopted since over a year is sealing those areas or providing additional coating to transform and further protect the surface from corrosion. So those let's say, high activity areas where you would normally expect to see corrosion to start are reduced or sealed away. So this is basically a summary of the suit, why basically FNC is suitable for the application. What is interesting here is that on the right-hand side, you can see probably the metallography, and the metallography really shows a cast iron, a gray cast iron, which has been nitrided. So very difficult to make out the white layer on top, but it's there. On top, there isn't much different background. It's sort of grayish, but this is just the way the sample has been mounted. And inside the structure, what you can make out, those gray flakes are basically graphite flakes. And this is why cast iron is called gray cast iron, because part of the carbon content, which is relatively high in this type of cast iron, well, part of this carbon will appear as flakes, and those flakes will play an active role in the way the material behaves. Well, also it is very important to say that cast irons do mature. It's a very special group of materials. During cooling, after casting, there are many transformations going on, phase transformations. Of course, there is a physical cooling down and stress formation. So if you would machine and then subject the rotor or the disc to very high temperature in nitrocarburizing, which is usually around 1070 degrees Fahrenheit, or about 570 degrees Celsius. It could be slightly different, but it's usually between, let's say, 560 and 580, rarely up to 600. Then all those stresses would come out, and you would have a disc that loses its geometry or undulates. This is why typically before Ferritic-Nitrocarburizing or before even machining, the discs are subject to stress relief operations. Those stress relief operations are obviously done at a temperature that is higher than the process itself in order to prevent any warping. So we did many tests. We did some. Sorry, going too fast here. So the test we have done is different stress relief operations done at approximately 630 degrees Celsius or 1166 Fahrenheit. And we did nitrocarburizing at 570 degrees Celsius, which is 1058 degrees Fahrenheit. Sorry for that typo. And we followed those trials by a series of tests to see how the discs will behave. So just a small disclaimer, it's very difficult to take hardness measurements on gray cast iron because you have all types of formations. You have graphite, you have iron, obviously you also have perlite and so on. So depending on where you go or what's under the surface that you're indenting with the Vickers micro-hardness tester, you may have variable results. But in essence, what you can see here is that you do have a nitrided case depth in the Ferritic-Nitrocarburizing, which is much better than you would expect, let's say, in the carbon steel. And the hardness of the material has really relatively improved as well. As for roughness, roughness will always increase after nitrocarburizing. It does increase as well after nitriding, and the amount of roughness increase that you would expect varies on the original roughness. So basically the rougher the surface, the increase of roughness may be exponentially higher. If the roughness is relatively low, this roughness increase will be much lower. However, there is a threshold under which you could have almost mirror polished surfaces. Basically the growth of roughness will remain approximately the same, similar at least. So there is a sweet spot probably for roughness, and it just shows that that we try to limit, and we can limit in the process increase of roughness, but it always still depends on starting roughness. In manufacturing operations, depending on tooling, if it's brand new or a bit older, a bit more worn out or less, you may have different types of roughness in the same within similar batches from one day to the next. Therefore, it is very difficult to keep track. Okay, so this is one of the tests that we have done for wear, and as seen here, nitrocarburizing has reduced somewhat wear and wear rate. What we call a Smart ONC, which consists of a further surface modification on top of white layer, shows a slightly higher wear rate. However, the areas of this coating did not really affect the base material nor the rest of white layer. So what we can expect from as a conclusion is that we have, yes, lost some of the Smart ONC or the final sealing process, which is basically a sealing post-oxidation process, but other areas would normally maintain an improved corrosion resistance. So away from breaking areas, the disc would still corrode less than it would not have been processed that way. Now, this is an interesting study because it shows friction. Here, at first, you try to interpret this. Of course, the blue line, in case you cannot make out the colors on your monitor, the blue line, which is at the bottom of the top diagram, is just pure gray cast iron. And this gray cast iron appears to have a bump in the middle, but probably it is has been caused by accumulation of wear material and should not be really relevant to the study. Of course, it has a coefficient of friction that appears to be lower. And one of the reasons that really explains that is that, as such, gray cast iron is considered a self-lubricating material. What happens is that due to the presence of graphite flakes, it will form, graphite will form a what we call a tribofilm, a very fine film between the two contact surfaces that will lubricate the pin. So you're trying to wear out a surface, but you are actually riding on lubricated surfaces. And this is why apparently it has a lower coefficient of friction, but it's not necessarily better for breaking nitrocarburized surfaces seem to offer a better grip, even despite post-oxidation, which in theory at least should lower the coefficient of friction. One last note on that subject is that typically trials are done at higher temperature. Here, all the trials that we had access to were done at ambient temperature. So the way that nitrocarburized discs would really react at temperature, they will really warm up or heat up, sometimes become even red, will perform differently and will perform differently depending on the type of mating pads. So since the elimination of asbestos, what you see is now, or NAO, non-asbestos organic pads, which are kind of common in North America. They don't really perform extremely well at very high temperatures. So depending on the country and driving habits and even use of vehicle, you'll see semi-metallic or ceramic pads. For instance, high usage vehicles such as, let's say, taxi cabs, buses, police vehicles, delivery vehicles will use a different type of pad, but this type of pad would not be very good if you're using only a few times a week your car, because most likely the pads will disintegrate slowly in humidity. You're not using them basically as much as you should. On the other hand, vehicles that are being used in higher speeds also have different brake pads. In electric vehicles, typically the nitrocarburized solution is used for rear brakes, because the rear brakes are mostly underused and they are really play a stabilizing role. So let's say if you stop accelerating, the first thing will happen is that you will regenerate power, and this will be your first braking experience. And then you'll have to use eventually the front brakes, especially for extremely fast braking or if you really need to stop fast. So those brakes will see a higher transfer of weight, see more work, and obviously more heat. So the formulation of front disc brakes and pads in electrical or hybrid vehicle and rear ones is really different, and this is what you should look at. So the layer basically performs extremely well, but its final quality of performance depends on the way it is being used and which brakes it is being used for. Now, one of the last corrosion tests that we have done, and this is very interesting, is okay. Typically, one disclaimer here. Typically, for vehicles, this test does not really represent working conditions. This is a standard salt spray test, which is common in metallurgy, but vehicles are subject to different media pollution. So there is eventually alkaline attacks, caustic or acidic attacks on the brakes. So this is completely neutral, and therefore not completely duplicating real working conditions. However, you can use this test just to assess the difference or different reactions of different surface finishes to corrosion. It still is a baseline. It is still a baseline, and this baseline is critical because it allows us to see if improved, for instance, improved post-oxidation called the Smart ONC works better than regular FNC or regular FNC plus regular post-oxidation. And this is of interest because we can provide ourselves with some feedback. So what you see on top here is just gray cast iron, Ferritic-Nitrocarburizing, ONC, which is post-oxidation, Smart ONC, which is the improved post-oxidation that seals those defects in the white layer, among other things. So after 20 hours, basically, you have a huge coverage by corrosion on both gray cast iron and Ferritic-Nitrocarburizing, while post-oxidation and this improved post-oxidation display extremely good results. We see almost no corrosion whatsoever. After 68 hours, just gray cast iron and nitrocarburizing fall out completely of the race. They are completely corroded. So the post-oxidation or regular post-oxidation lasts through 100 and 148 hours and even gets to 268 hours. At interesting point, at 148 hours, you don't see a sign of really corrosion on this improved Smart ONC process, which starts to rust only at 268 hours and finally gets to 360 hours with relatively good results. So it is much better than all the previous treatments. This is a comparison of untreated cast iron, painted cast iron, which of course paint works in different ways, just insulating the surface from corroding agents, but it is very short-lived and corrosion very often starts under the paint. Then you have Delphi Technologies zinc flake coating. It's a very interesting coating because it offers anodic protection. So it is a chemical protection. And then you have Nitrex improved Smart ONC, which shows, which is of interest, zero corrosion at 100 hours, which is already better than the zinc coating somehow, and displays some corrosion at 312 hours, which is comparable or better than a zinc flake coating. Now, a few words. I'm sorry, that went a bit too fast, but why not? Okay, so well, what I wanted to say basically is that once you move away from our metallurgical lab or experiments that we do here in Montreal, what you see behind me is not the real background. I am in the plant. What happens is that you have to have extremely high productivity ratios with very heavy components, of course. So you have to treat literally millions of discs every year, and all of those discs are very heavy. So you may have to maintain as well a quality of surface finish, a productivity rate, and somehow stay competitive because automotive or transportation industry is extremely competitive. So what you see first is a tip-up furnace, which was the type of furnace used since the very, very beginning of FNC treatments for brake rotors in North America. I believe the first trials ever for those treatments were done in a similar setting. So it has several advantages, obviously, and some drawbacks. So as you can see, the volume of the furnace, which is huge, allows for the treatment of very large quantities of rotors. Hopefully, if the process succeeds, you have very good results. Obviously, also there is a risk associated with problems during the process, so you may eventually lose part of that load. However, the big advantage is productivity rates. The other big advantage is that you can see it's sitting on a very solid sole, which doesn't show here very well, but there is circulation fans, so to maintain uniformity of temperature. So you can put humongous loads of rotors in one load, and the furnace will take 50,000 pounds perhaps of load easily. The negative point is that obviously it is very hard to heat up and to cool down, so the process time is really affected by this construction. It is not really very easy to automate. So it has to be loaded with lift trucks and unloaded with lift trucks. And as such, it's not really adapted to an expansion of production into much higher quantities. One of the unseemingly competitive solutions is a horizontal batch furnace. Now, horizontal batch furnace don't seem like it, but they have very interesting advantages. They can be automated in the sense that the doors may open by themselves, which they do. We have many assisted doors, so when the furnace is prompted to, has finished its process, or it's ready to take a load, it will unlatch itself, open, and wait for a charge car, for instance. We have also a construction with horizontal doors. So the door may open horizontally, and you may easily load and unload the furnace without using a manual loader. So it can be automated. Secondly, the design of a retort furnace allows for a reduction of ammonia consumption. And this is very important because ammonia is derived mostly from natural gas. And natural gas, for instance, in Europe is very expensive now. So it is one of the factors. Obviously, if Inconel 600 is used in the construction of a furnace, it will further reduce the consumption of ammonia and increase lifespan of the furnace. So you can also increase the number of furnaces if your production rate increases. So you are flexible in a way, and you don't have to have a continuous line which is really oriented towards one product. However, what you can see here is that we have been building those cells, and we are not the first ones, probably not the only ones doing that, but we have been building them since, now here we say more than 15 years, definitely early 2005 or 6, we built the first one. What's interesting here compared to horizontal furnaces or batch furnaces is that, of course, they can be automated, but this is the most efficient method of treating extremely large quantities of rotors past a certain threshold of production. So if your threshold exceeds, for instance, 2 million or 3 million rotors, depending on the size of the rotor, obviously, then this is the most viable solution, because they can be automatically loaded, unloaded, don't need personnel, and can work within a complete setting that is what we call lights out. So humans are expected to be there just to eventually oversee loading or unloading operations, but those are usually done by robots. What we show here is one of the variations, because there are different types of furnaces we build. The number of chambers, first of all, is dictated by the length of the process. So if you want 15 microns of white layer, and the process will be shorter, we'll need less chambers. If we need to produce more than 20 or 25 microns of white layer, then the process will be, of course, longer. So being longer, obviously, you need more chambers to remain productive, and this dictates your stroke or takt time, as it is known in the industry. This is just a general configuration as an example, but it's probably one of the better solutions in extremely high volume manufacturing settings. This shows, I'll go very fast because we're getting towards the end of the presentation, but this is an expansion of the same concept with, on one hand, nitrocarburizing furnaces, and on the other hand, on the right-hand side, actually, stress relief furnaces. So very much on the top and the bottom of this diagram, what you see are basically robots loading and unloading fixtures. So you have a cell of discs going in and discs going out. On the right-hand side, it's the same, except those are just as cast. So they are going into stress relief for perhaps floor to floor more than 3 hours. And they are heavier because they have not been machined. And they come out, they got machined, and they return to the nitrocarburizing cell. All what you see in between are holding tables, or we call them magazine tables, transfer tables that, of course, allow to bypass also one side or the other of the installation and allow for maintenance or manual loading in case there is a problem with the robots, for instance. This is one of the example of robot nests and one of the examples of load fixtures. Most of those fixtures look similar. Why? Because they allow for very easy loading and indexing of each arm. Also, they will allow to maintain the discs in a horizontal orientation, so they will not warp. Most manufacturers require for the discs to be in this position in order to prevent warping. And obviously, you can design the fixturing, separate fixturing for all types of discs manufactured. However, it makes things easier, less efficient, but easier to have one design. So it's really a question of choice and the number of models that you are planning to nitrocarburize. Well, this shows very rapidly how it's integrated on a larger scale, because there is an MES system. So basically, this is the your manufacturing execution system that is more or less on the plant level, and then Rotor 9800 or Cumulus system, which is your SCADA and your intelligent solution for running the cell itself. So your plant may have an MES. Then we have at a lower level within the cell a Rotor 9800 or Cumulus system, which provides management of all the incoming, outgoing disks and loading, unloading operations. Of course, also operating the charge cars automatically, and reporting all the data from the furnaces themselves. Now, the furnaces work with process controllers and interface with the system using PLCs. It's also the case for the charge cars. So this allows you, obviously, for a part traceability and intelligent or maintenance that will allow you to foresee upcoming equipment issues or maintenance issues, and also will allow you to predict if your processes are going along with plant quality. Of course, this is validated by a metallurgical lab, which is not automated. However, it allows you at a glance to see if you're going into the right direction. So the system is run by Cumulus, which has the SCADA system, but it is a artificial intelligence and Internet of Things enabled system, which has a higher ability to reduce labor and predict eventual maintenance. So this is a summary of the advantages of equipment. One word, because obviously this is on the practical application. One word is that we are heat treaters. So we have been not only building but also operating this type of furnaces for many years. And experience basically dictated this kind of approach and this kind of evolution in equipment. So this would be the conclusion. I'm running a bit over time, but as you can see, there is a huge evolution in heat treating that follows the evolution of transportation, and not only because we see also FNC used to replace hard chrome plating, for instance, following the REACH legislation. So you see, we follow now Euro 7 legislation. So we are basically also growing up, adapting ourselves to a transformation and improvement of nitrocarburizing and similar technologies. Thank you very much.
Okay, Jack, thank you so much for that great presentation. So this is Katie again, Global Spec moderator. We are going to move into asking Jack some questions that we have from our attendees. The first one I have for you today, are all gray cast irons comparable?
Oh, thank you very much, Katie. No, they are not. In this case, we're talking about gray cast irons. You also have nodular cast irons. You also have carbidic cast irons. So there are very many different types of cast irons. For this application, mostly those are gray cast irons, but even those have variations in the composition. Chiefly, the variation is in the quantity of carbon. So you'll see higher carbon content, and higher carbon content will mean more graphite, but it will also mean slightly softer discs, and you see less carbon. And obviously, both variations will influence the thickness of white layer that you obtain, because the diffusion is affected by the quantity of graphite and carbon.
Okay. Jack, thank you so much for that answer. All right, our next question here. All right, Jack, this person is saying some questions about FNC. Number one, post-oxidation. Is it requested by OEMs? Number two, is FNC enough for fulfilling Euro B11 regulations?
Thank you very much. Okay, so first part is that not all OEMs specify post-oxidation, and some of the OEMs hesitate as far as oxidation goes. It is true that when we perform post-oxidation, the corrosion results are much better. So there is definitely an advantage. Now, some OEMs may choose to do only FNC and keep on coating or painting the discs with their zinc flake paint, for instance, and stay completely away from post-oxidation. Others may just want oxidation or very light oxidation for aesthetics, or because their customers are used to. If you take a very known electric car made in USA, the discs appear a bit blue or bluish, and it's sort of their trademark. Okay, so there are many different reasons besides corrosion that may play there.
Okay, great. Thank you so much, Jack. Appreciate that answer. So as I mentioned to the attendees, we have lots of great questions. We will get through as many as we can in the next about 8 minutes or so. If you do not hear your question being answered, we will reach out to you following the webinar. All right, our next one here, Jack. I understand the concern about brake lining particulate emissions, but what is the concern for brake rotor particulate emissions? Rotor material should almost entirely be iron or iron oxides, which are non-toxic and ubiquitous in the environment.
There is a concern overall about all the particles, because the size of the particles makes them impact your health. Yes, iron, it is true, is neutral. somehow, but if you go under a certain size of particles, those particles will penetrate, go into your system, into your bloodstream, and pass different barriers. So it's not necessarily very good to breathe iron dust or oxide. Now, what I mentioned before also was that this apparent iron oxide is not a big issue. It's more the pitting that appears within the disc. Now, most of the pitting, and there is a way of seeing pitting, but you'd have really to see under microscope. This pitting creates holes that do work as a grate. So basically, they're grating away the pads. So it's not what you necessarily see, but how the corrosion works, because corrosion is really corrosion is not uniform and it is selective. So the pitting issue is at the heart of those emissions, and not necessarily iron oxide.
Okay, great. Thank you so much. All right, so we do have time for a couple more questions here. As I mentioned, a lot of these will be answered after the webinar is over. Since we have so many of you participating, we appreciate it. These are great questions. All right, Jack, our next one here. I wonder why we see higher hardness in FNC compared to FNC-ONC or Smart ONC.
Okay, part of this is the type of test. It's the material is very hard to test, but on average, and I believe we don't have enough averages in this graph. On average, what happens is that with FNC, you have you have a structure that has not been through post-oxidation. Post-oxidation will further modify the surface, but the way it is done, there is no nitriding media or nitrocarburizing media. Therefore, and it's done at high temperature. So therefore, you may be losing some of the very fine white layer. You may be losing or creating some very fine porosity, which will reduce what we perceive as hardness. So, it's just superficial. It doesn't really change in depth. It's just the white layer itself, and really beyond a few microns, there won't be any impact.
All right, great. Thank you, Jack, so much for that answer. So our next one here, this person is asking, with higher surface roughness after FNC, is it recommended to deburr the parts after FNC?
No, it's not. It hasn't been done in the past. The roughness that is apparent will most of it in case of a gray cast iron comes from the graphite flakes. What happens is that as the white layer builds, as diffusion builds, there is stress applied on compressive stress applied on the structure. So basically those flakes will start standing up like hair on a cat's back and stick out. So you'll see more roughness, but the roughness will wear out extremely fast because the material is very soft.
Okay, thank you, Jack, so much. We've got time for a couple more questions here. Again, if we don't get to your question, we will reach out to you following today's webinar. And then just a note to take a look at some of the widgets along the bottom of your attendee console. There are some widgets down there that you might want to take a look at before we end things today. You can hover your mouse pointer over those. And we have a couple resources listed in the resource list just below Jack's bio. Now would be a great time to grab those on your way out today. All right, Jack, we've got time for about one or two more. So let's take this next one here. How would the application of Smart ONC differ between passenger vehicles and heavy-duty trucks?
Okay, you are breaking up a bit on my side, but this very heavy trucks so far, in most designs, don't use discs. They do use drums, or at least on the rear wheels. Just in the front wheels, you have discs, and some constructions are moving towards discs for easier service, but it's not really general. I would say that it does not really make a difference between passenger vehicles that much and trucks. What is important is the type of brake pads being used, because commercial vehicles tend to be using different types of brakes, and it's still to be evaluated what kind of benefit there would be. Obviously, you have to remember that Smart ONC, at least on the brake surfaces, the brake pad surfaces, the brake pads basically will remove that surface relatively fast. What stays behind is that the other areas of discs will remain protected against corrosion, and this is obviously the same for all kinds of vehicles. What is important is the diffused nitrogen and the amount of white layer which tends to remain there after quite a long time.
All right, Jack, thank you so much for that answer. So this is going to be our last question for today. We are at the top of the hour. So for anyone whose question was not answered, we will reach out to you following the webinar. All right, and this question, Jack, like I said, this will be our last one today. Is there a correlation between the surface roughness and corrosion resistance of the FNC treat rotor?
Yes, there is, and it's a general remark. This applies to hydraulics as well. It applies, which we do FNC quite a bit. It applies also to brake pistons as well. The idea here is that very rough surfaces tend to maintain corrosive liquids. So obviously, if you have humidity accumulating, your surface tends to maintain those liquids instead of helping them run away. So the lower the roughness, the better corrosion resistance, and the higher the roughness, the worse corrosion resistance.
Okay, Jack, thank you so much for that last answer. We are going to start to wrap the webinar up right now. So I want to say a huge thank you to Jack for being here with us today, presenting live and taking so many of our attendees' questions. So Jack, thank you so much. It was a pleasure.
Thank you very much, Katie.
All right, and a huge thank you to all of our audience members today. Take care, and we will speak with all of you soon.